Okay, well, thanks again to everyone for coming back to the Foundations of Probability seminar. And happy to have today is Konstantin Genin from, we'll say, Tübingen, talking about simplicity and scientific progress. So go ahead.
Yeah, thank you so much. Thank you for the invitation. And yeah, I'm sure everyone, like I said, has a lot on their mind at the moment, so I'll try to distract you. Okay, so title, now it's working. So if you read the Ilkka Niinilaoto's SEP article on scientific progress, he has this first cut in a taxonomy of 20th century philosophy of science. And his first cut, he classifies them into the synchronic and the diachronic school. So the synchronic school is focused on the finished products of science, according to Niinilaoto, and the diachronic school is focused on scientific change. So I like this distinction because I finally, when I first read it, and I recognized that I had a home finally in the diachronic school, and it gave me a kind of cozy feeling. But I want to alter the distinction a little bit. So here's my how I'm cutting up the field, and just this is probably not well. Okay, so I'll see what you think. So we have synchronic schools in both philosophy of science and epistemology, and in philosophy of science, the kind of exemplar case is confirmation theory. In epistemology, it's evidentialism. And then in the diachronic schools, maybe slightly less well known, I want to say that learning theory is an expression of diachronic philosophy of science, and virtue epistemology is like diachronic epistemology.
Can I ask a question? Sorry, what is virtue epistemology?
Yeah, so I'm going to do that.
Oh, okay, thanks.
So what is confirmation theory? So confirmation theory that we know and love is it would be finished if we could just come up with the right notion of confirmation, which is a relation between evidence and theories, which if you knew the right confirmation relation, you would know exactly how well supported some theory is by the evidence that you have in your hand. Now, evidentialism in epistemology is very similar. Evidentialism is about evaluating your doxastic attitudes, and ultimately it's how what you're interested in is, do my doxastic attitudes fit the evidence, right? So the locus of justification is theories and evidence, or my beliefs and my evidence. But you change the focus when you go to epistemology. It takes on a diachronic field because what you're interested in is characters. You evaluate characters with respect to intellectual virtues. So you're evaluating an entire character, which is like a disposition to change your mind, or there are various kinds of dispositions that you carry through your entire life, basically. And in learning theory, it's similar. You're not looking at the relationship between evidence and theory. You're looking at to justify methods by virtue of their learning behavior or their learning dispositions. So I want to put a little bit of love in the upper right-hand corner today. So here's Loudon in the Introduction to Progress and Its Problems. And I think this could be like a manifesto for the diachronic school, although basically don't agree with Loudon about anything else. But I like his rhetoric here. So Loudon says this: progress necessarily involves a process through time. And rationality, on the other hand, has tended to be viewed as an atemporal concept. And most writers see progress as nothing more than the temporal projection of a series of individual rational choices. But we may be able to learn something by inverting the presumed dependence of progress on rationality. So maybe so according to this synchronic school, what it is to be progressive is to be rational at every stage, and maybe you conditionalize or something like that. There's some right way of conditionalizing, and that's all there is to progress. But maybe we reverse it and we say, well, what it is to be rational is to cultivate a disposition that is progressive. A similar kind of move is made by Jonathan Kvanvig in his book. Jonathan Kvanvig is like, someone you'll read about if you read the SEP article on virtue epistemology. And he says this: it's far from obvious that the best way of structuring a fruitful cognitive life is to concentrate on individual time slices and whether knowledge or justification is possessed at each such time slice. and let the totality get generated by cementing together these time slices. So he's arguing against this kind of synchronic view that Loudon was sketching. So if you're in the synchronic school, the main problem is the problem if you're in the diachronic school, the main problem is the problem of progress. Like, why is scientific method conducive to progress? Or can it be made conducive to progress? Or is it already conducive to progress? Something like that. Well, the most famous diachronic theorist maybe of the 20th century is Popper, and he had a story about this. And he says, science progresses through a series of highly testable conjectures, followed by dogged attempts at refutation, right? And personally, I'm a fan of this. It's like it's a philosophy of science for existentialist heroes who eschew the comforts of confirmation and who are always trying to, knock down their favorite theories. But the worry about this is why think that this is going to lead to anything than a series of bold mistakes yielding to new and bolder mistakes, right? That essentially is Lakatosh's objection. He says, Popper offers a methodology without an epistemology or a learning theory, like no reason to believe that this is going to go anywhere. Of course, Popper knew that and was aware of this objection, and he hoped to show that his critical method leads to theories of increasing truth-likeness, where what is roughly one theory is more truth-like than another if it has more true content and less false content. Of course, his notion was famously trivialized independently by Pavel Tichy and David Miller, and this led to a long and interesting, fruitful research program in truth-likeness, making more and more sophisticated attempts at a definition of truth-likeness. But the problem is, from my perspective, is even if you had the right notion of truth-likeness, you wouldn't have any, guarantees. It wouldn't help you. It doesn't demonstrate that science yields more truth-like theories. You just have a definition of what truth-likeness is. No reason to think that the critical method yields more truth-like theories just because you have a definition of truth-likeness. And basically, Laudo admits this. He says, the problem of estimating verisimilitude is neither more nor less difficult than the traditional problem of induction. So it's kind of a reduction to a harder problem. And I think the way out is kind of to pull this virtue ethical maneuver. So here's Zagzebski kind of describing the virtue ethical maneuver. Since justifiedness is a property of a belief, it's very difficult to adjudicate disputes if the belief is treated as the bottom level object of evaluation. Instead, we focus on the deeper concept of an intellectual virtue and treat the justifiability of belief as derivative. So we're not talking about beliefs, but we're trying to move up a level to character and virtue, that kind of thing. And so similarly, instead of focusing on theories and what makes one theory more truth-like than another, or what a progressive series of theories would look like, we're going to focus on what a progressive method is. So what's a progressive method? And it's a very naive idea. A method for answering a question, some question under discussion, is progressive if the chance that it outputs the true answer is strictly increasing with sample size. We're imagining a statistical sampling kind of thing. And it could just be like, as you get more information, data, evidence, your disposition to output the right answer is improving. And notice that notion makes sense, even if it doesn't make any sense to ask which of two false theories is closer to the truth, as long as one of them is true. But okay, if you don't like, there's actually a role for truth-likeness. Maybe you think none of the answers are true, but that's okay, because you can say a method for answering a question is progressive if and only if the chance that it outputs the most truth-like answer is strictly increasing with sample size. There we could use the output of this research program, truth-likeness.
Can I ask you a question? What do you mean by chance? Where does that chance come from?
Yeah, so what I mean is whatever frequentist statisticians mean when they mean by chance, it's something like,
statisticians usually don't know what they mean by chance. I don't know what you want to mean.
Yeah, so I would take like chance metaphysics as somehow basic here, like since it's like the folk metaphysics of statistics and the science, and I'll just say whatever it is, the chance that it's your disposition to output the truth. It's the degree of your disposition to output the truth.
I mean, someone thinks that chances would apply, let's say, to just repetitive events like coin tosses would be very
Yeah,
puzzling.
I have in mind, of course, IID sampling in the back of my mind. And I was saying, okay, if you think, IID sampling, I don't like that. Okay, but I'm just going to try to make some story work for some version of, statistics. And then, other smarter people can generalize it away from IID sampling.
So Casey, I have a related question.
Yeah.
So, I mean, what if you're at the instead of being a frequentist, what if you're a Bayesian here, but you're of this school that all models are wrong. So like the truth doesn't lie anywhere in your hypothesis space. Then then you can't be progressive because every scientific answer is false.
Yeah.
Right?
So if you think all models are false, some are just more useful than others, that's okay. You still want the disposition of your method to be improving as you get more data.
Some notion of utility. So either way, you have to have some notion of truth likeness or utility that.
Yeah, if you think all models are false, but some are more useful than others, then there is some most useful model, let's say, or at least let's posit that one of them is the most useful that you're considering. You would still want your method to have the following property. As I can collect more data, it's more likely in some sense that I will get the most useful one. What if you didn't have that property? That means it's actually a bad idea to collect data, because as I get more data, I could be, it's the likelihood that I get the best theory is getting worse.
No, that part seems right, but the problem with making it about utility is that utility is personal, and so each scientist could be following a progressive path towards more and more useful answers, but every scientist is diverging from every other scientist as they each find the progression towards the most useful.
I mean, personally, I would prefer to put a realist spin on it, but that's how I worked everything out. The true answer, or the most truth-like answer. I suspect there's a version of the story that would work even for not as subjective as Bayesian exactly, but the kind of Bayesians that worry about consistency properties, not probability one and subjective probability consistency properties, but in the frequency sense of consistency. And that's most Bayesians. Most Bayesians, if you offer them a prior that's not guaranteed to converge to the truth in any of or in some very small, it's only guaranteed to converge to the truth in some very small set of the possibilities, that I think they feel some pressure to move to a different prior, unless they're hardcore subjectivists. Anyway, so I don't want to, it's not like I can adjudicate the dispute between realism and instrumentalism here. I think in my mind, when I'm working out the results, I have just a naively realist picture, but I think some version of the story, it doesn't really depend on that, as long as there's something it means to improve. If there's some goal of inquiry, there's something it means to, your disposition to get the goal is improving over time. Right. That has to make sense for whatever goal you pick.
Yeah, I just question whether there's a common goal among distinct scientists with distinct priors. But
I don't think.
Yeah, but fair to stipulate the realist assumption.
Yeah. Okay, so progressiveness would be good. That just means that the chance or whatever, the likelihood is strictly increasing as sample sizes are increasing. But you can't have literal progressiveness for most problems. But you can have almost progressiveness, alpha progressiveness. So say that a method is alpha progressive if the chance that it outputs the true answer never decreases by more than some small alpha. So here, this is just a very silly picture, but it's meant to just give you a picture to have in your mind. Here on the x-axis, we have sample sizes increasing, and then I'm graphing the probability that you've got the right answer. If you have large dips, like you have on the right, that's a less progressive method than you have on the left, which has only small dips. That means that collecting a larger sample is never a terrible idea. Although on the right, sometimes it looks like getting a bigger sample is a bad idea because you have a dramatic dip in the probability of getting the right answer. So the idea is never dump the truth. If your method is not progressive or not even alpha progressive for some small alpha, what you have is a built-in failure of replication, because here on the right, in the picture on the right, at some point you have the high probability of getting the right answer, and then you get a larger sample and you have a lower probability of getting the right answer. So you've built in a kind of tendency to fail to replicate true results, not false results, true results. Failing to replicate false results is good. Failing to replicate true results is bad. And so I think this is a fairly straightforward idea with a nice philosophical pedigree. It reminds me anyway of Socrates and the Meno. Why is knowledge better than true belief? It's kind of got a stable quality to it. And okay, so what would that look like in some examples? So imagine what does a failure of progressiveness look like? Imagine you're proposing a study to recruit 100 patients to test whether drug A is an improvement over the standard treatment B. You do your pretrial power analysis. You say, well, if drug A is significantly better than B, the chance of detecting the improvement is 60%. And the funding agency says, okay, 60%, that's pretty good. They approve the study. You find the result, and that's great. Now you propose a replication study. Now we're going to recruit 150 patients to try to replicate this thing. And if the drug is significantly better than standard treatment, the chance of detecting that improvement is now 40%. Doesn't seem right. Why would you expose more people to potential side effects for a worse chance of finding the truth? It's like, not only is it perverse from an epistemic perspective, it also seems perverse from a moral perspective. Surprisingly, many textbook frequentist hypothesis testing methods have this perverse behavior, meaning that the probability of rejecting the null hypothesis correctly, it converges to 1 in the limit, but it does so in this sawtooth fashion. It doesn't do that monotonically. And at some sample sizes, it looks like getting a larger sample is a bad idea because the dip is kind of dramatic. So this is from Chernik and Liu's paper. So one.
Sorry, Casey, what's the reason behind that? It doesn't look. I'm just trying to get some intuition behind this.
Yeah, so it's kind of surprising. Why does it happen? It usually happens for discrete distributions where you're trying to achieve a certain significance level, like let's say 0.05. Sometimes at some sample size, because the distribution is discrete, you need a discrete cutoff. So you can never achieve the significance level exactly, 0.05. Sometimes you get very close, like 4.9%. But then at a higher sample size, because of the discreteness, you can either get 5.1%, which is not good enough, or something very dramatic like 1% or 0.01%. So to meet the significance level, you sometimes have to overshoot, and that results in a dip.
I see. So, but this seems to be more of an artifact that is that pertains to perhaps these specific setups that has to do with the continuous versus discrete distributions. But I had thought that perhaps you had something in mind that's more structural to perhaps the design of the study or.
Yeah, I mean, this is just one way in which it could happen. Failure of progressiveness is everywhere. It's not just in hypothesis testing. It's in basically every statistical method for inferring anything. And you'll find it in causal inference methods. You'll find it all over the place if you look. Most people don't look. And I'm just saying, here's one place I found where statisticians were paying attention. And they found it in this simple hypothesis testing case where the reason is easy to understand. But it's actually ubiquitous. I mean, I looked at, for example, recently, Lingham methods for inferring causal direction from observational data. And they have this property all over the place, although you can avoid. I mean, the question is, can you always have this property? Or are there some times when you just can't have it? And the answer is it's in between those two things. Sometimes you can have it, sometimes you can't have it. And I have a bunch of theorems about it. So
I'm sorry, while you have that graph ahead, I mean, you alluded to this before, but isn't there a complementary problem with, if you just look at the probability of a type 1 error on the y-axis instead of the power, that the probability of a type 1 error is flat with sample size. It's not progressive at all. And that's a common criticism of frequentist tests.
Well, there's nothing stopping you from achieving monotonically decreasing significance levels if you want. And there's no, I mean, yes, it's weird to insist on 0.05
Right.
at every sample size.
Exactly.
But
no, I mean, it's an artifact of the tradition of assuming a fixed.
it's just some
level,
tradition of fixed alpha, yeah. And you don't have to. Nothing's stopping you from sending alpha to 0. In fact, I think you should.
No, but the point is that increasing sample size doesn't increase your knowledge. It keeps your probability of type 1 error flat, which actually, this is consistent with your story, does seem perverse.
Yeah, I agree with that. And you should send alpha to 0. Yeah. But can you do these things? First of all, that will make this other problem harder. So there's all these trade-offs. If you want alpha to go to 0, that might, if your schedule for sending alpha to 0 is too aggressive, on the other side, it will create these extreme kind of non-monotonicities in power if you're too aggressive. So there's some kind of trade-off here, and you have to manage it. It's honestly, when you do it, it's kind of tricky to manage, because what is the right schedule of sending alpha to 0 so that you don't have huge non-monotonicities in the power elsewhere? So there's like a whole like mathematics of this that like people don't usually talk about. I don't think anyone talks about, honestly, but except for this one paper that I found.
Sorry, I do want to, just to follow, I do want to point out there is a concept in statistics talking about estimators called self-consistency, exactly, basically to prevent estimators to have this behavior. Namely, that if you collect more data and you were to apply the same procedure, you're never supposed to end up with a worse estimate. It's called self-consistency. I think it's very related to
yeah. I actually never looked at it for estimators, and I suppose for estimators you can recreate all these things. I looked at it in hypothesis testing, model selection, but in estimation I never looked. So thank you. Yeah.
So the example you're giving here about power makes it seem like the issue is, I mean, you know, getting to the truth, you know, either of the hypotheses could be the truth.
Mm-hmm. I'm just showing you.
It's not clear what getting closer to the truth is.
Here we've stipulated that some possibility in the alternative is true, and now I'm looking at the disposition to get it right over time. I'm just showing you that I'm not like imagining things that this never happened. This happens, and it's kind of ubiquitous. So progressiveness sounds like such a...
The method is not, well, okay, but the method wasn't designed for that assumption that something in the alternative is true. I just make that comment.
So I'm just saying, you can look all over the, you know, at any parameter. It should be progressive everywhere. I'm just showing you, pick one, and I'm now graphing the probability and showing you that it isn't progressive here. And so because progressiveness sounds like such a weak property, more data is better. Like that sounds like duh, of course. Doesn't every statistical method have that property? The answer is no, not every statistical method has that property. And the failure of that property is kind of ubiquitous.
So you want it to be, I mean, if you think of it in terms of parametric statistics, you're looking for something that you want to be, you want a certain kind of monotonicity to hold for all parameter values.
Mm-hmm. Yeah.
So a Bayesian certainly agrees with more data is better. In fact, Bayesians can prove that experimentation always has positive value. The information you get has positive value. So is that right? That Bayesian inference is not perverse by your account?
No, well, they just think that they're not perverse. Are they perverse? Yes. At probability 1, I'm not perverse.
But what are those probabilities? I mean, from if their probabilities are the right probabilities, then they're not perverse.
Well, it's their opinions. I'm not talking about their opinions.
So I think what you know, Barry, I think he's asking for a lot more than what the Bayesian offers. He's asking for the posterior probability of the true value always to go up? No, no, clearly it doesn't. Yeah.
You can't always go up. It's the expected value, but for a Bayesian, it's expected if he gets more data that the true value.
Oh, well, okay, but that's not what he's asking for. That's not.
All right, no, I see that. I see that.
Well, it's not quite
Yeah.
the same. For a Bayesian, as you get more data, the posterior is going to get more peaked around a true estimate. It's not necessarily.
No, I mean, first of all, there's no guarantees. I mean, so if you have Cosma Shalizi has lots of papers where if there's, there's old papers from Friedman that sometimes Bayesians don't converge at all. Their posteriors don't concentrate on the truth at all. So they're not even consistent from a frequentist perspective. And sometimes, they'll just bounce between, in the limit, they'll bounce between concentrating on one thing than another one. So Cosma Shalizi has a lot of these examples like that. So it's not guaranteed that, and of course, Bayesian inference is like any other inference. Like you concentrate on, if you're doing model selection and it's a difficult problem, your posterior will concentrate on one thing and then it'll crash and concentrate on some other thing. And it'll crash and concentrate on some other thing. So it's not like Bayesian inference is this magical thing where like you just build more and more and more on the truth or something like that. That doesn't happen. Bayesians are like the rest of us, have to make mistakes, right? Anyway, so here's a
I
theorem.
understand though, I'm just not following you. So it's right that Bayesian inference someone following Bayesian inference can make mistakes and they might get misleading evidence because they get misleading evidence. But I was just pointing out that prior to doing the experiment, the Bayesian couldn't argue to himself that doing the experiment has expected value.
Yeah, okay. I mean, I don't know. I can't prove a theorem to you how those things are deductively related. From some subjectivist perspective, it's a good idea to get more data, but your objective probability of getting the right answer could go down, and those things can be consistent with each other. And it's just a disagreement about which things we care about more. Do you want your objective probability of getting the right answer to increase? I mean, there are frequentists in the world, and they want it.
What do you mean by objective probability?
Well, what does anyone mean by what does a frequentist mean by objective probability? What does
I have a whole view about that, but I don't want to hear that.
I just mean I want to basically I'm saying like, okay, there's a lot of frequentist practice in the world, and I don't want to tell them what they mean by chance. I just want whatever they mean by chance, I want it to improve as they get more data. Yeah. I don't think I owe anyone a theory of objective chance. I mean, it's gonna hold for any interpretation of probability. The theorems are good. They're good. They're real theorems. If we can get to them. But so one thing is, just for the case of hypothesis testing, it's a special case. So long as you have a consistent hypothesis test of the thing, then there is an alpha progressive test of the hypothesis for every alpha, meaning you can get these non-monotonicities to be arbitrarily small as you want. You can get the wiggles down. You can get them down smaller than this. You can get them down even smaller. You can't get them to 0, but you can get the wiggles to be arbitrarily small. Well, so here's another example. That was hypothesis testing. Here we have causal inference from non-experimental data. So I got my PhD at CMU with Clark Gleamore and Peter Spirides, and they have this causal discovery program. And their causal discovery algorithms are strongly guided by a kind of Occam's razor, which says that sparse graphs are preferred, and you only introduce causes or arrows when sharp conditional independencies are refuted. It looks very like Popperian kind of. You prefer the highly refutable sparse graphs, and you posit sharp conditional independencies until you refute those independencies with hypothesis tests. And they prove that several algorithms converge pointwise to the true causal equivalence class as you get more data. But there are infinitely many other algorithms that are pointwise consistent, but would give different results on finite samples, drastically different results. Some of those would even reverse the preference for sparsity. You can prefer the complex graphs until sample size 10,000, and then switch to the Occam method, and you would still have pointwise consistency. So what justifies using their methods, or what justifies using natural methods that posit sparse graphs and then only introduce edges when they have to? This is just a version of the Carnap critique. So Carnap says, Reichenbach is right. Any procedure which does not converge in the limit is inferior to his rule of induction. However, the same holds for an infinite number of other rules of induction. Therefore, we need a more general and stronger method for examining and comparing any two given rules of induction. And in the case of causal inference from observational data, they acknowledge that there's no you don't have any of the usual comforts, the things that narrow down the class of justified methods to just the natural ones. They say most of the algorithms we have described require hypothesis tests. The parameters of the test cannot be given their ordinary significance. Neither the significance level, nor the power of the test measures anything interesting about the search. And furthermore, uniform consistency is provably impossible to achieve given the usual assumptions. So the situation looks something like this. There's uniform consistency. What does uniform consistency mean? It means I can a priori compute a sample size by which the objective chance of getting the right answer is as high as I want. So give me a bound on error, and I can give you a sample size by which I achieve that bound on the probability of error. That's uniform consistency. Pointwise consistency is this other weak thing way up at, can you guys see the pointwise consistency? It's blocked for me. It's over here. Way up at the other end of infinity, there's pointwise consistency, and it doesn't have any of that property. It just says that whichever parameter is the true one, whichever possibility is the true one, you converge in chance to it, but you can't say when, and you can't say when you have. At any finite sample size, for all you know, you've converged. For all you know, you haven't converged. For all you know, it's going to take 10,000 more years to converge. So pointwise consistency is very weak. And there's not a lot of stuff in the middle. There aren't many norms in between these things. So uniform convergence is something everyone wants, but you provably can't have. Pointwise consistency is like this really lame consolation prize that like you want, but no one is satisfied with. And so my proposal is progressive convergence is a strengthening of pointwise consistency, which is achievable for difficult problems like causal inference, but short of uniform consistency, and which narrows down the class of admissible methods to the natural ones, actually. So, oh yeah, that's kind of what I just said. Progressiveness is feasible in causal discovery, even though uniform convergence is not, under the usual assumptions. And it gives a new interpretation of the error probabilities in the nested test methods. Essentially, carefully managing them is necessary for ensuring progressiveness. And here's a theorem for my dissertation for typical problems. And I don't have the technical goods on the table yet to define what I mean by typical. There exists an alpha progressive method for every alpha greater than 0. So for typical model selection problems, I owe you an explanation. It's just a placeholder for now. You can converge to the true hypothesis, true model, or best model, and you can get the wiggles to be arbitrarily small. Moreover, all progressive methods must systematically prefer simpler or more falsifiable theories. And of course, I owe you a story of what simpler means and what more falsifiable means. But basically, the moral of the story is that a carefully calibrated neo-Popperian methodology can ensure progressive convergence.
So Casey, can I ask here that when you talk about convergence to truth or the chance or the increase of the chance, however chance is defined, it seems like it's some kind of a number that's assigned to a hypothesis or a statement or a state of the world.
No.
Whereas
that's Bayesian thinking. If you fix the world, that fixes the chances. Chances are like dispositions of things to happen in the world. So if you pick a world,
sure. So
you don't have chances on the world. That's Bayesianism. That's subjective probability. We're talking about objective probability. So you do have an understanding or an interpretation of chance as opposed to what you said too. It's not subjective probability. Whatever the thing is that when you go to frequent statistical conferences and they're talking about it, that's what I mean. It's generally speaking, if they're not a Bayesian, They're talking about objective probability. Some kind of
So
disposition.
let me ask you this. When
Yeah.
you say that you want a higher chance of converge of the truth, if you're taking the increase in the P, or a decrease of the p-value, or the increase of power, you always are talking about the probability of given h naught or h a or something.
No, I'm just saying
Of
in
seeing the
every,
data.
what I mean by progressiveness, whichever model is true, whichever parameter is the right one, pick one. Whatever one you pick in that possibility, your disposition to get the right answer has this property where it doesn't go down by much as you get larger.
But
samples.
one of those worlds is true.
Yeah. I'm saying whatever one is, it's true for all of them. If this one were true, you would have this property. If this one were true, you would have this property. If that one were true.
I guess I'm just not quite understanding how we can take an expression of P of data given H to be a chance of converging to the truth, because it seems like the statement is
There's no chance.
backwards.
There's no chance of converging. Convergence and chance is that for every, you fix a probability, and then the probability that you fix a P, fix a distribution. Now look Pn, P, like you sample from P n times, n1 times, n2 times, n3 times, right? In every world, your method has some disposition of outputting has some probability of outputting every hypothesis. And whatever the true one in that world is, you want that disposition to be, we could just it'd be clearer if I just did the math, but I thought it would be, maybe I should just skip to it so I can give you the statement. Uh-oh, what happened? Maybe this is a less, I wasn't sure what the audience would be like, so I didn't put in the most technical definition, so I'm having trouble finding it. But what I mean is, you're a frequentist. You think there's no parameters, fixed chances, and you don't have probabilities over parameters, right? Pick a parameter. That tells you what is true. Because if you fix the parameter, you fix the model, that's answers the question that we're interested in. No matter how you do that, no matter which one you pick, it fixes the objective chances in the world. And so what you want is that whichever one you pick, the objective chances of outputting the true answer in that world in here is improving over time. Is that okay? It's like you fix a world that fixes which answers are true. In every world, whichever one it is, the disposition of your method to get the right answer in that world.
So I think I understand what you're saying is that you are letting the sampling distribution of the data combined with the statistical procedure, which is defined as a function of the data, to together dictate the randomness that is in the output.
Yeah.
I think my question actually surprisingly came down to the same one as Barry was asking, which is, when we have a frequentist procedure, what is the number that you're taking out of there to represent the so-called chance that's assigned to the worlds? Because the p-value, the power, none of those are.
No, you don't assign any chances to worlds. It's just a chance of outputting. Let's say we're doing model selection. Suppose one of the models is true. Now pick a parameter in that model. You want the probability that your method points to the right model, the true one, to be increasing with sample size.
I think I understand what you're saying, but it's only sounding like something. It sounds like you're talking about, as you say, model selection or classification.
Model selection is causal inference. So I'm thinking my paradigm case is like you want to solve some social science problem, and you're trying to do causal inference from data.
But you aren't allowed, your answer is not going to be a interval.
It's going to be a model. Yeah, it's going to be a causal DAG or something like that. It's going to be some answer.
So you're going to choose, so you got some set of possibilities and you're going to choose one. So in a general sense, it's a classification problem you're looking at.
Classification is like, I want to know if the picture is a cat to me. I'm not talking about classification. I'm talking about model selection. Classification problems, I don't know, maybe we use words differently, but classification problem to me is like, I'm looking at, I want to train some doohickey to classify pictures as cats or non-cats or something like that.
But if I understand right, you have a set of possible DAGs and you want to use one.
Yeah, so if you fix the
you don't want somebody to say,
well, in the limit, I want to converge to one. I want to eventually, it should be informative. It should be informative eventually. I'm not saying you can't suspend judgment at
so you wouldn't look at, okay.
Maybe you could give a simple example of how this works. I mean, the simplest I can think of is, let's say there's some hypotheses about the objective probability of a coin landing heads when flipped.
Yeah, let's say we're talking about the coin is fair. We're interested in whether the coin is fair or not. If the coin is fair, my probability of conjecturing that it is fair should go up with sample size. If the coin is not fair, my probability of conjecturing that it is not fair should go up with sample size.
But you're not looking at problems where you have a continuous scale and you want to locate the truth on that scale, because that would be too demanding. You aren't going to get to an exact number, right?
Yeah. The examples I have in mind are like model selection problems. And it's just model selection. It's nothing. It's not something really hard like estimation. It's only picking the true causal DAG that's generating the data. It's like, it's kid stuff basically.
So you puzzled me by the way you answered. So you talked about the probability of your conjecturing, but why think that there's an objective probability of your conjecturing?
If your method is driven by data and there's distribution.
Maybe you also have some sort of funny brain disease, which makes the probability of your conjecturing something other.
Yeah. So here I'm talking about data-driven, the probabilities of various data-driven methods.
So it's some condition, the probability of you uttering certain sounds given something.
I mean, the U is maybe it's just English that's conspiring against me. I mean, we usually program our computers to output various conjectures on various different data sets. We, like a bit of scientific metaphysics is that there's some probability distribution governing the data. The methods are a function of the data. So that induces a probability over the methods saying various things, since there's probabilities over the data.
So there's a probability distribution over the computer printing out, whatever the...
Exactly. If you assume that there's a probability distribution of the data, there's a probability distribution over the possible outputs, the conclusions that the computer will come to.
Okay, that would have been, right, if I understood that at the beginning, that's what you were doing, it would have been...
Yeah. That's why I mean methods. I mean statistical methods. Yeah, it wasn't a metaphor. It's just, I'm talking about methods that we use to infer things, statistical methods. And they have if they're data driven, there's some probability for them, for everything that they could say, there's some probability that they say it. Objective probability, not subjective probability.
Just to be clear, you're not only saying that they're data driven, right? You're also saying that the choice of conjecture totally supervenes on the data.
Yeah, well, methods, that's how every single statistical method is. What people
but you might think scientific theorizing more generally is...
What people do with the methods, I agree, is not data driven. But I'm talking about methods. What people do, we should at least have methods that have this property. It'd be weird if we couldn't at least agree that the method that we recommend for studying this or that question has dispositions that are improving over time. That seems to be the kind of thing that a group of inquirers in some scientific field should be able to agree on.
I don't think anybody's disagreeing with that. It was rather the unclarity of what is the probability that you were talking about is the probability of. But now I understand it better. It's the probability that the computer or the person will give a certain answer, assuming that it's only given the description of the problem and what and the method, and nothing else. So you're, as Alex was saying, it doesn't depend on anything else.
A
Doesn't depend on
statistical method,
cosmic
yeah. I
rays
just
or-
mean the things that's how every single statistical method is. Any kind
Well,
of
it may be.
statistical package
But
that
of
you
course,
use in
the
R or
objective-
anything like that.
That may
Yeah.
be, but the objective probability of the computer giving a certain response
Mhm.
might also involve the objective probability of cosmic rays hitting the computer.
Yeah. Well,
So I just said if you would express things in some way so that that misleading thought wouldn't have occurred, at least to me, I wouldn't have been misled.
okay, I'm sorry. I'm clearly misleading everyone. Anyway, well, can I carry on, or are people
Mhm.
still unhappy with me? Anyway, what I was hoping to say was, so if you believe my theorem that all progressive methods must systematically prefer more falsifiable theories, by progressive, I think hopefully I've cleared up the model I created, then you have a kind of justification of Occam's razor. What is Occam's razor? It's a systematic preference for more falsifiable theories. And that is a necessary condition of a certain kind of progressive convergence to the truth. So kind of along the way, what I hope to pick up was an epistemic justification of simplicity preference. So traditionally, here is Baker in his SEP article on simplicity. He's saying, he's kind of despairing. So traditionally, epistemic justification has been synchronically conceived. Justifying an epistemic principle requires answering an epistemic questions. Why are parsimonious theories more likely to be true? And that kind of, that if you frame the problem that way, it leads to kind of despair, because here's Loudon saying, no one has shown that any of these rules is more likely to pick out true theories than false ones. It follows that none of these rules is epistemic in character. But who said that the only way to justify a simplicity preference was to show that at every sample size, the simpler theory is more likely to be true in some sense? So what the theorem is saying is that a systematic preference for simpler theories is a necessary condition of a diachronic feature of inquiry, meaning you want the probability that you output the right answer to increase over time, or almost increase alpha monotonically.
Casey, sorry to interrupt again. Can you tell me, in your definition of simple, a pair of nested regression models, which one is simpler, the larger or the smaller?
Yeah, so it only makes sense. I owe you a definition of simplicity, but that's in the later slides. It only makes sense for competing hypotheses. So linear is simpler than quadratic, and not the other way around. For nested models, the simplicity relation is not defined.
Isn't linear nested and quadratic?
I mean, when you make them incompatible, you mean like the quadratic term is non-zero. That's what I mean by quadratic.
Do you have a different slides where you actually do write down the math so that the
Yeah.
mathematician sides of us could understand it from that point of view?
Sure.
Maybe
I mean, you would have to you would need to have like a lot of patience with me, because to get that far, it requires a lot of setup, unfortunately. So what I hope to do anyway was to illustrate the result in a kind of simplified setting where we didn't have to bring in chances at all. It was a kind of, the way that these results were originally developed was you don't even do chance. You just assume that you get data and that refutes certain hypotheses. And in that case, there's, these kinds of qualitative results about progress are pretty easy to prove. And then there's a kind of topological analogy. You prove the results in, kind of this old-fashioned philosophy of science land where you get data that refutes possibilities. And then there's a topological bridge where you can translate those results to statistics. And the analogy is good, is a sufficiently good structural analogy that all the results still hold. Why topology? I mean, now I'm despairing because it looks like, okay, let's try it. Topology, if you look in the Wikipedia, it's defined as a kind of like rubber sheet geometry or something like that, where a coffee cup is equivalent in some sense to a donut because there's a continuous deformation of the one into the other. And that's kind of interesting, but it sounds irrelevant to epistemology. So I think topology needs a different interpretation. Topology is actually the logic of underdetermination. So what topology is really good at is capturing the structure of underdetermination in a certain problem. And hopefully, well, we'll see if I can prove that to you. And so we have some set of possible worlds. Now, I just mean possible worlds are just like the epistemic possibilities that are relevant in the context. So these can be parameters of a model. These can be possible worlds in the way that modal logicians understand them, but the way the statisticians understand these things is parameters. And we have a notion of a propositional information state. This is the mythological propositional information state that refutes certain possibilities and is only consistent with some. And here we're imagining that we're getting data with bounded error. We're trying to, like, let's say, estimate a certain parameter, a two-dimensional parameter, but it's not statistical. The idea is that you get information state, an open set, like a box, that's telling you that the true parameter lies in here. Obviously, this is a myth, you know, it's a kind of allegory that I'm telling you. And okay, so let fancy I be the set of all possible information states that you could encounter in inquiry. In this case, if all we're doing is getting bounded error measurements of a two-dimensional parameter, that could be like the set of all open rectangles. And I of W, if you pick a particular parameter or a particular world, is the set of all open rectangles containing W, the set of all information states true in W. And I of W restricted to E is the set of all true information states at W strictly stronger than E. Now, what's the intended interpretation of this thing? We say that E, this information state, is in the local information basis at W if, what I want you to have in mind, a diligent inquirer in W will eventually be afforded information at least as strong as E. Now, three axioms governing the information states. There's some information state true in every world. That's kind of analytic. Now, this one is non-analytic. It's a kind of accumulation axiom. Each pair of information states true in W is entailed by a further information state true in W. So here we have the green and blue. They're both true in W, and there has to be a red information state that entails them both. So information states are like the kinds of things that if you were looking left, if something happened. So what I mean is they're kind of like reproducible effects. They're not things like if I was looking left, I could miss forever what was happening on the other side of me. Information states are reproducible effects. No information is ever lost for good. And the last axiom is that there are most countably many information states. Well, if you need an argument for this, well, an information state is the kind of thing you could express in language. And, you know, there's the most countably many things you can express in any language. You can write it down. You can, if you want, you know, an argument, you could say a Turing type argument where well, go to Turing, and this is okay. Now, okay, so an interior point of some hypothesis. So we say that a world W, like this red world W, is an interior point of the hypothesis H, the red hypothesis. If there is some information state in the local basis at W, verifying H. All that means is, well, why is W an interior point of H? It's because there is an open rectangle where true at W, containing W, entailing H. And now we can define the usual topological operators. They take on they're like modal operators. The interior of H is the set of all interior points, which is just the proposition that H will be verified. because this is the set of all worlds where there is some information that you get that a diligent inquirer would eventually get entailing the hypothesis. And the closure of H is the proposition that H will never be refuted. So for example, the salmon color is the interior of H, and the closure of H is like everything red plus the blue boundary, because these are the sets of worlds where if information takes the form of an open rectangle, the hypothesis H will never be refuted. Because, well, I lost my annotate thing. If you live here, you'll eventually get a rectangle entailing that. But if you live here, all rectangles you ever get will be consistent with H. So this is in the closure of H. And so is this. Clear. For some reason, it's not letting me advance the slide.
So what is it that's countable? Would you remind me?
The set of possible information states. And so in the statistical case, yeah, the set of possible information states. Yeah. So all, if what we're doing is measurement, let's say, the set of all possible measurements you could ever get is countable. So what it's basically saying is you don't have infinite precision measurement. You have only finite precision.
So H is something that is countable or finite, is that right?
No, H is a set of possibilities. It's a set of possible worlds. It doesn't have to be countable. The set of possible information states is countable. So if we're talking, oh no. Yeah, the set of possible information states is countable. So it's the kind of data, information, the kind of things that could come in as inquiry, possible measurements, possible observations, and there's only countably many of them that you could get. Is that okay or no? Hello? Can you guys hear me? Okay, sorry.
You're good.
Okay. And now we can partition the worlds and the boundaries here. The frontier of H is the proposition that H is false, but will never be refuted. It's this blue part of the boundary. And the frontier of H complement is the proposition that H is true, but will never be verified. You can sort of see, like if I lived here, I would only, and then information takes the form of open rectangles, H is false, but it would never be refuted by an open rectangle. And if I lived here, it's true, but it would never be verified because I could never rule out H complement. God, it's not letting me advance the slide. No, here we go. So those are modal operators, and we can now define structural features of hypotheses. So we say that a hypothesis is open or verifiable if it entails its own interior. What does that mean? Recall that the interior of H is the set of all worlds in which H will be verified. So this is saying if H, however H is true, it will be verified. And a hypothesis is closed if the complement is open. So how do you say that? If the complement is open, that means however it's false, it will be refuted. And it's decidable if it's both. If it's both, however it's true, it will be verified, and however it's false, it will be refuted. Of course, everyone knows that most interesting scientific hypotheses are neither verifiable, refutable, or decidable. But there's a slightly more, slightly fancier notion that actually captures a lot of, I think, an interesting feature of scientific models. You say something is locally closed if it's true, it becomes refutable. So what do I mean by that? So suppose H is true in this way. Well, then eventually I get information verifying H. So it's kind of trivially refutable because it can't be false anymore. If it's true in this way, eventually I get information such that in this, like if you restrict to the information, H is now closed in the restricted topological space. In the restricted space, H is now closed. So that's how is this a feature of scientific models? For example, suppose we don't have nested models, we have competing models, linear, quadratic, and so forth. Linear is not verifiable because, well, let's say quadratic is not verifiable because if the truth is linear, you never get any information verifying quadratic, of course. However, if the truth is quadratic, eventually linear gets refuted if we assume a certain kind of nice data that we're getting. Eventually, linear gets refuted, and you know that if quadratic is false, I'll see a sign eventually. So scientific models have this feature, like if they're true, they become refutable eventually. There's a kind of guarantee. If quadratic is true, it will be refutable eventually. And so from on Popperian grounds, it will be okay to conjecture it because it will become scientific. Doing this thing again. There we go. So here's a very simple example. So we're talking about Hume, and Hume is worried whether bread will always nourish. And we're going to abstract from all features of time. The only features of the world we're interested in are, will bread always nourish, or will it fail to nourish someday? So let bread be the world in which bread will always nourish. Now let scary bread be the world in which bread eventually fails to nourish. If you live in the nice world, the only information you ever get is going to be consistent with both hypotheses, because for all you know, the next day it will stop nourishing. If you live in the sad world, you will eventually get this information state, the tighter information state. It will be in the newspaper, bread doesn't work anymore. So what we defined here is the simplest, interesting topological space, the Sierpinski space, in which all information consistent with the nice hypothesis is consistent with the sad one. But the converse is not true. There is information in the sad, the scary bread that refutes nice bread. So we have a kind of asymmetry on which we can hitch simplicity.
Okay, did I misunderstand something? Did you say that if a theory is true, it will eventually become refutable?
No, that's not in general true, of course. It's just a nice feature of certain kinds of theories.
So that could be the case for some theories, right?
Yeah, it could be the case for some theories. In statistics, you have to kind of translate everything because it's refutable as a kind of allegory, but yeah. So let's see an example of a locally closed hypothesis. So suppose we're going to make the story a little fancier. There's three possible worlds: the world in which bread always nourishes, the world in which bread stops nourishing, it nourishes for a while and then stops nourishing forever, the skull, and then this the second one, it's where bread takes a vacation and then eventually gets back to work. The vacation can be arbitrarily long, right? So this is the world in which bread stops for a while, but then it goes back to being good old bread, working forever. This hypothesis, let me see if that's strong. This hypothesis is refutable. If it's false, it will be refuted. This hypothesis is not refutable because if it's false in this way, it won't be refuted. All information will be consistent with it. However, it does have the property that if it's true, you knock out this hypothesis eventually, this possibility gets knocked out, and it becomes refutable. So if it's true, it will become refutable because it's just the old picture again. Is that okay? And a theorem that you can prove is that, sorry, all the little things are blocking my view of the slide, so I keep having to move them around. So something nice that you can prove, you can characterize the locally closed property. So if something is locally closed, if its frontier, which is the set of worlds in which it's false but not refutable, is itself refutable. Maybe that's too fancy for us. And now introduce slightly fancier ideas here. So something is limiting open if it's a countable union of locally closed things. So it's like a collection of these articulations. Articulations are the kinds of things that if they're true, they become refutable. And a countable union is like a collection of articulations. It's kind of like a paradigm. It's like, however it's true, it becomes refutable. And something is limiting closed if its complement is limiting open, and it's limiting open if it's both limiting open and limiting closed. We'll see some examples. God damn. advance the slide, please. Okay, so here's an example. Suppose we have competing paradigms. There's a polynomial paradigm. This school of thought thinks that there's some polynomial that's generating the data. And there's the trigonometric polynomial paradigm. They think it's a cyclic phenomenon. And so it's some trigonometric polynomial that's generating the data. And these people think, the polynomial paradigm, people think it's a trend, some kind of trend. The question we want to answer, let's say, is which paradigm is true and what is the degree of the polynomial that's generating the data? Now, what would this actually look like? So suppose the truth is that it's a linear polynomial. Both of these paradigms are consistent with any data that you'll ever see. So there's always going to be some polynomial and some trigonometric polynomial that's going to capture that will fit the data, right? If it's linear, what it'll look like is, well, you can fit some linear, or you can fit some very kind of more complex trigonometric polynomial, and then as data accumulates, you're going to have to make more and more ad hoc maneuvers on that side, fit even higher degree trigonometric polynomials. You'll always be able to fit some trigonometric polynomial, but what it'll look like diachronically is like that paradigm is making a bunch of ad hoc maneuvers or something like that. They're going to lose grad students, and these people are going to be very smug because their linear hypothesis has been holding up forever. Now, notice something. Intuitively, if it's linear, all data you'll ever see is compatible with quadratic. So linear is simpler than quadratic. Any pair is decidable. Data will eventually decide between these two, but all data, but the paradigms themselves are not ordered with simplicity. They're in a cycle because all data compatible with this one is compatible with that one, and the converse is also true. So they're in a simplicity doesn't decide between the paradigms, but it decides between the articulations in a paradigm. Linear is simpler than quadratic. The same is true on the right, but any pair is decidable. Now, what do I mean by Occam's razor? So according to Popper, more falsifiable hypotheses are simpler. Now let's start over here. Recall that the closure of B is the set of all worlds where B will never be refuted, and the complement is the set of all possibilities in which it will be refuted. This is saying if B will be refuted, then A will be refuted. Now we're taking the contrapositive. If A won't be refuted, then B won't be refuted. And then by a simple result in topology, this is equivalent to if A is true, then B won't be refuted. So Popper's notion is really this one. A is simpler than B. If A is true, then B will not be refuted. Okay, it's got some nice features. It's motivated by the problem of induction. It depends only on the structure of possible information that you might get. It's independent of notation. It's independent of parameterization. It doesn't depend on prior probabilities. It just depends on the structure of underdetermination in your problem. But it has this annoying problem, which is that logically weaker hypotheses are less falsifiable. It's just a trivial fact that if A entails B, then A entails the closure of B. So logically stronger hypotheses are always more falsifiable, always simpler. And so the suspending judgment is like the maximal violation of Occam's razor. Occam's razor, is forcing you to be opinionated, which is wrong. There's a simple way of fixing this problem, which is that the lack of falsifiers is bad only if B is false. So just say A is simpler than B if A entails that B is false, but will never be refuted. And that captures the simplicity order. For example, bread will always nourish is simpler than bread will eventually stop. In general, universal laws are simpler than the set of exceptions to that law. Linear is simpler than quadratic. So it returns to us our usual intuitions in a lot of cases. But there's another issue. Gerrymandered hypotheses can still obscure simplicity relations. So the true law is linear or the cat is on the mat is no longer simpler than the true law is quadratic. And we just have to bite the bullet here and say something, which is that our response is that A is simpler than B if A is consistent with a possibility in which B is true but never refuted.
So it doesn't solve this doesn't solve Goodman's problem.
Oh, no. I mean, well,
That's
it depends
what
what you
you
mean.
have.
Yeah. It's so if you frame a question, green versus some exception to green, green is simpler. But if you pick out a GRU, GRU T, then GRU T is simpler than the set of exceptions. So it's only returning to you the structure of underdetermination in your space. So it's not going to say green and GRU T are just not ordered because they're decidable. Information eventually decides the question between green and GRU T. So it won't say that green is simpler than GRU T, although it will say that green is simpler than GRU and GRU T is simpler than not GRU T. But green and GRU T are just not ordered by simplicity. Okay, what is a method? A method is a straightforward thing. It takes in propositional information and makes conjectures, outputs, conclusions. What does it mean for a method to converge to a hypothesis? It just means that in a world, W, there exists some information E true in W, such that for any further information true in that world, the method continues to output H. So it stabilizes to H eventually on information. And say that something is a limiting verification method for a hypothesis is if H, it converges to H if and only if it's true. So if it's true, it will converge. And if it isn't true, it won't converge to H. It might do something else like oscillate forever. This is a very weak inductive notion of success. It's like William James. It's like no bell in us tolls to let us know for certain when the truth is in our grasp. The method never gives you a sign that it has converged. All you know is that it will converge. It might have converged already. It might converge in 1,000 years. And a limiting refutation method for H is just a verification method for the complement. A decision method is something that's both a limiting verification method and a limiting refutation method. Now we can strengthen this idea to like get deductive methods. So a verification method for a hypothesis converges to it if it's true and otherwise suspends judgment if it's false. And furthermore, it's monotonic. As it gets more information, it never takes back any of its conclusions. So you know from all these properties that as soon as it says something non-trivial, that H is true. So it rings a bell when the truth is in its grasp. And a refutation method is a verification method for not H. A decision method is both. The cool thing is that levels of Borel complexity, which are measures of topological complexity. What I'm showing you is a hierarchy of inclusion. Everything that's clopen is clopen and open. Closed and open are not included with each other, but everything closed is limiting clopen. This is a hierarchy of topological complexity. And the levels in this topological hierarchy of topological complexity correspond exactly to how methodologically accessible a hypothesis is. If it's open, there exists a verification method. If it's closed, there exists a refutation method. If it's limiting open, there's a limiting verification method, the kind of inductive method that never rings a bell, but is guaranteed to eventually converge to the truth. And so you can prove this theorem. Now, what is a question? A question just partitions the possibilities. You can have fancier notions of questions, but for now, it's a simpler one. Now, we know what simplicity is, but what's Occam's razor? You can prove that the following are equivalent. Infer a simplest relevant response in light of the evidence. So what I mean by that is restrict to the evidence, and then output a conclusion that's simplest given that evidence. Infer a refutable relevant response compatible with your evidence. What I mean is restrict to your evidence and given that new topological space, pick something that's refutable. Or infer a relevant response that is not more complex than the true answer, whatever the true answer is. So err on the side of simplicity. This refers to the data E to the evidence E. So does this one. This one seems kind of magical because it's like always err on the side of simplicity. That sounds like I need to know what the truth is. I never convert, but these are actually all equivalent. And that comes up in statistics because in statistics you can come up with a statistical version of number 3, but coming up with statistical versions of number 1 and 2 looks impossible because the data never restricts the set of possibilities.
But Casey, can I ask you, so just to check my understanding, simplicity, you mean the latest, the third definition you gave for simplicity, that A is with front.
Although if A entails that B is false, but will not be refuted, I think that one's easier to think in your mind, and it's equivalent for almost every single question you'd ever come up with. So morally you can use it, but it's not ultimately, that's not what we go with.
Okay, and also by equivalence between principles, they would all use the same conjecture, no matter which question you're given and which data.
Oh no, it's just whenever you satisfy one, whenever you're inferring a simplest thing, you're also inferring a refutable thing, and you're also, if you always satisfy one, then you never err on the side of complexity.
I see. Okay.
Yeah. So yeah, it doesn't mean, I mean, there could be many ways. There could be many simplest things. It doesn't narrow down the answer uniquely. If some certain problems, there could be many simplest things consistent with the data.
I see. These are all 3 properties that the principles can have, and then you are saying satisfying one is the same as satisfying the other.
Yeah. Now, an empirical problem is just the collection of all these things. It's a set of possibilities, and then you've partitioned it into a question. And then it also specifies what kind of information is available. Well, is potentially available. Like if it just specifies all the possible ways inquiry could continue, could be driven by information. And let Q of W be the answer that's true in W. So for example, if W, then Q of W is green. If this is W, then Q of W is green. A solution is a method that, wait, what happened? This looks wrong, but a solution is a method that converges to the true. In every world, it converges to the true answer in that world, whatever it is. I think I wrote it down wrong. But a solution is a method that in every world, it eventually converges to the true answer in that world. And a problem is solvable if and only if it has a solution. Now here's a theorem. A problem is solvable if and only if every answer is limiting open. What does limiting open mean? It's a countable union of locally closed hypotheses. Locally closed things are the kinds of things that if they're true, they become refutable. They're like articulations of paradigms. So the most difficult solvable problem, in the sense that you can converge to the truth and the limit, is a paradigm dispute between countably many paradigms. And many different people have proven this theorem. So we had it in 2015. Of course, Kevin Kelly had it in his book back in the 90s, but not in this extremely general topological way. Debrecht and Yamamoto in informatics in Kyoto, I think, had it in 2009. Our friends in Amsterdam had it at the same time as we did. So now we can define progressive methods, at least in this mythological setting of information that refutes possibilities. Say that a solution is progressive if and only if for all information states in I of W and for all further information stronger than E, if your conjecture on E entails the true answer, then your conjecture on further information also entails the true answer. In other words, the true answer is a fixed point of inquiry. Once you have the truth, you don't let it go. Once you have the true answer to the question that you posed, more information won't knock you off of the truth. This is a qualitative version of the statistical thing that I was trying to describe before. So here's a, can you achieve this? Well, there's certain cases in which you obviously can't achieve it, right? if I'm asking you something like, how many fundamental particles? No, sorry. Are there an even or an odd number of fundamental particles in the universe? And then we have a simple model of inquiry where like we notice another one because we smash things together faster and faster, and eventually we notice another one and we say, oh, it's 3, oh, it's 4, it's 5. Obviously, you can't have a progressive solution to the even and odd problem because, well, if it's even, you'll say even, and you'll say odd, then you'll say even, and you'll say odd. But you can have a progressive solution, the intuitive one, to the how many fundamental particles are there question, right? Because you'll say 1 until you see 2, and then you'll say 2. But you'll never say, if 3 is true, there's a method that avoids saying 3, then 2, and then 3, or then 3, and then 4, and then 3, right? You don't have to do that. And here's the theorem. If there exists an enumeration of the answers agreeing with the simplicity order, meaning you never put a simpler thing after, if A is simpler than B, you put A before B in the enumeration. If there exists such an enumeration, then there's a progressive solution. Now, even odd, there obviously doesn't exist a progressive enumeration because everything, they're in a simplicity cycle with each other. Everything consistent with even is consistent with odd. Everything consistent with odd is consistent with even. Any way of ordering them, you put something simpler later. But if you go 1, 2, 3, 4, 5, that's fine. That's an enumeration agreeing with the simplicity order, and you can solve it in a progressive way. And every progressive solution obeys Occam's razor. Now, what's the argument for this? It's kind of, so let me show you a simple example. So here we've assigned the boundary to H. And given the orange information, H is simpler because all information consistent with H. So H is the frontier of H complement is not equal to 0, not equal to the empty set, because these worlds are in the frontier of H complement. They're worlds in which H complement is false but never refuted. But the converse is not true. If H complement is true, you eventually get information refuting H. So in this case, once we've assigned the boundary to H, red is simpler than blue. I should have said that the whole time. Red is simpler than blue. So suppose you get this information, which is consistent with both red and blue, and you conjecture blue. And here's Occam, and he's scolding you. That's not the simplest answer compatible with the information. So now I will prove to you that your method can't be progressive. Now, pick a possibility in the frontier, this one. Since you're a solution, there must be some information on which you conjecture the truth there, H. Otherwise, you wouldn't be a solution. I have to be able to pick some rectangle on which you change your mind to H, some stronger rectangle. But since that's in the frontier, that's compatible with some blue possibility. And so now I can show you this information, nested information, on which you have to go back to H complement. So that looks like I was cheating, but all I did was prove to you that there's a set of nested information states, all of which are true in this blue possibility, in which you dropped the truth because you went from H complement on the weak information to H on the slightly stronger information, and then back to H complement. So you drop the truth in that world. I mean, that is morally, that's the argument. So showing this is the easy part. The necessity is usually easy, but possibility is difficult. So I won't prove that theorem.
Sorry, I didn't quite follow. Why did you go to H in the second rectangle?
Yeah, so I have a bunch of annoying notifications blocking my view, sorry. So every progressive solution obeys Occam's razor. What does it mean to be a solution? It means in every possibility, there's some information state on which in that world you converge to the true answer. Here the debate is between red and blue. So pick a world in the frontier of blue, this one. Since you're a solution, there must be some amount of information true in that world on which you would conjecture the right answer. So that's just an existence proof for this rectangle, that some such rectangle exists on which you say H. Now, since this world is in the frontier of blue, that information state must be compatible with blue. So there's some further information, this one, on which I can refute H and force you back to H complement, to blue. So notice what happened. It's violating Occam's razor doesn't hurt if, so this is an argument for preferring simplicity. It's easy to give an argument for preferring simplicity if the truth is simple, right? But it seems like you have to always rob Peter to pay Paul. Like preferring simplicity helps in simple possibilities, but hurts in complex ones. But here, what happened was, here's a complex possibility in which you failed to be progressive because you violated Occam's razor by jumping ahead of Occam. Okay. All right, so here's Elliot Sober saying for an earlier version of this kind of result. That story may be okay if the candidate theories are deductively related to observations, but when the relationship is probabilistic, I'm skeptical because everything I just told you is a fairy tale. Like you never get any information refuting anything. So this whole thing is just some joke, right? You never get these open rectangles refuting all the possibilities outside of the open rectangle. Everyone knows the statistical hypothesis. Every parameter, you know, any bias of the coin is compatible with any sequence of coin flips. So this is just foolishness, what I'm telling you. So that's the worry. Propositional information refutes logically incompatible possibilities. Typically, statistical samples are logically compatible with every possibility. But don't worry, there's a common topological structure in both of these cases. And so we can translate the results from before into the statistical setting. Before we had possible worlds, now we have probability measures over a sample space. Those are our set of possibilities. I mean, if you really want to do the full story with models, then you have to get a little fancier, but you just believe me that it works for models too. Models induce measures, but they are not themselves measures. Two models can be distinct even though they induce the same measure. So I owe you, like the real story is a little more complicated, but just.
Well, as far as we know that probability measures and the way we endow the topology of a space can be detached. You can have two perfectly okay different topologies that will classify different sets as closed and open differently. Nevertheless, you can still have the same probability measures specified and they would be related.
I need to pick out a special one for you that's privileged in some sense. So I owe you like a privileged topological space, which is the relevant topological space for what we're talking about. We know that we can put lots of different topologies over probability measures. You can have the
but would your classification for the hypotheses and models be different under the different ones, or because I'm thinking you're going to use, I guess, methods, statistical models to draw these conclusions, and that would be the same procedure regardless of topology.
I'm not sure because the models themselves are the conclusions. I don't use them to. I use methods to draw conclusions on the basis of data, and my conclusions are one of the models, or maybe I suspend judgment or something.
Sure. I mean, you're using a statistical method, which has its own specifications of probability and so on, which is different, which is detached from the topological specification of the underlying space.
Yeah, sure. Topology, we have no topologies at all yet. It's just we have some set of measures over some sample space. There's no topology yet.
Well, I thought what you just said was that the topology of the W space comes.
No, I have to get to the rest of it. So far, I haven't told you what the right topology over probability measures is. All I'm saying is that the analog of possible worlds is probability measures. But if I were to do the real story, it would have to be models. But I'm not doing the full story. It's just measures for now. So before we had possible worlds, they were like these abstract possibilities, whatever they were. Now they become more concrete. They're probability measures. Is that okay? Anyway, okay. I hope that's okay. Remember, we had a notion of what a verification method was. Now I'm defining for you a notion of what is a statistical verification method. A statistical verification method for some hypothesis at a significance level converges in chance to H if H is true. It powers up to reject if the alternative is true. And then it suspends judgment with high probability if H is false. So it's the kind of thing with if H is false, with high probability, it suspends judgment. It says, I don't know. And if H is true, it eventually converges to saying H is true. So it's kind of like a hypothesis test of H complement. And we say that a hypothesis, a set of measures, is statistically verifiable if and only if it has a verification method at every alpha. So you can drive alpha down arbitrarily low. That's saying like, this hypothesis is statistically verifiable if there exists a consistent hypothesis test of its complement for every alpha. And something is a limiting statistical verification method. That's all I'm doing is dropping the bound on error. It converges in chance to something entailing H if and only if H is true. So if H is true, it converges in chance to saying H. And if it's not true, it doesn't. And something is statistically verifiable in the limit if it has one of these, has a limiting statistical verifier. So recall the worry. It seemed like the only statistical information state was W. We're going to sidestep statistical information, and we're going to go for statistical verifiability and build the analogy at the level of statistical verifiability. So under a natural assumption that we can go into, there exists a unique and familiar topology, the weak topology, the topology of convergence and distributions on probability measures, for which you have the same hierarchy, meaning the open sets are the statistically verifiable propositions, the closed sets are the statistically refutable ones, the limiting open ones are the limiting refutable ones. So we've made a structural analogy with the statistical case in which topological complexity is capturing a different kind of methodological accessibility, where we basically added chances of error and translated convergence to convergence in chance. Now there are details to the story that I'm skipping, but so in both logic and statistics, by logic, I mean like traditional philosophy of science, where we imagine that hypotheses are refuted by evidence, we have that topological complexity captures methodological accessibility in some sense. How methodologically accessible a hypothesis is a feature of its topological complexity. So now I've built the topological bridge. You see, the analogy is topology, right? What's preserved is topological structure. Yeah, so you can start with, you can kind of like do good old-fashioned philosophy of science, imagining that evidence refutes possibilities, allow methods a small chance alpha of error here in the right way, and then you obtain the corresponding statistical inference over the topological bridge. You just import the logic stuff over the statistics, over the bridge. Now, a statistical question is just a partition of a set of probability measures into countably many answers. So this is like model selection, assuming that we have identifiability. That's the assumption. Model selection is just this. A solution to a statistical problem converges in chance to the true answer, whatever it is. So for every measure, if you do IID sampling from mu, the chance that my method outputs green converges to 1. That's what I mean by solution, whichever measure you pick. So recall, Occam's razor, we proved that the following principles are equivalent. Infer a simplest relevant response in light of E, that's Occam's razor. Then there's this Popperian thing, infer a refutable relevant response compatible with E. And the third one, error on the side of simplicity, infer a relevant response that is not more complex than the true answer. Now, I will do a statistical translation of this one because it doesn't involve compatible with E, the thing that doesn't work in statistics. Restricting to the data doesn't work. Restricting to information doesn't work. So I'm going to translate the third principle. What is a translation? The statistical alpha raiser, in each world and at each sample size, infer an answer more complex than the truth with chance at most alpha. So what I mean by that is, for all measures, the probability, and for all sample sizes, that my method equals, for everything more complex than Q of M, let's say, let H be more complex than the true answer at mu. Complex than Q of mu, the true answer at mu. Then the probability that the method outputs H is less than alpha. Sorry, that's ugly. But so for any more, so pick any measure, pick any sample size, the probability that at that sample size, your method outputs something more complex than the true answer Q of mu, why mu, because we picked mu here, the true answer at mu is less than alpha. That's our version of err on the side of simplicity. Why? Because in every possibility, at every sample size, the chance of conjecturing something more complex than the true answer is small. So probably you didn't violate Occam's razor. So a solution to a question, to a statistical question, is progressive if the chance that it outputs the true answer is strictly increasing with sample size. And it's alpha progressive if the chance that it outputs the true answer never decreases by more than alpha, let's say. And then here's a proposition. If there exists an enumeration that agrees with simplicity, there's an alpha progressive method for every alpha. So you can get the bumps arbitrarily small. And every alpha progressive solution satisfies Occam's alpha raiser, meaning the chance that it outputs something more complex than the truth is less than alpha. So it's a statistical version of this thing. I should probably stop there, but I'm just saying, for the problem of inferring the true Markov equivalence class of the DAG generating the data, there exists an alpha progressive solution, and it's going to be the one that prefers simpler DAGs. So it kind of answered Carnap's critique, right? Thank you.
Thank you.